The ventricles of the brain can serve quite an important purpose. But first, let's look at what they are and where they are located. So first off, we have 4 different ventricles in the brain. We're going to have 2 lateral ventricles, a third ventricle, and a fourth ventricle. Now, in this anterior view, you can see how the lateral ventricles are going to curl out and around. The third ventricle is dead in the middle, and the fourth ventricle then is a little bit lower down. The fourth ventricle, almost more of a diamond shape. From the lateral view, you can see how those lateral ventricles are really running almost the length of the brain here. So they really do take up quite a bit of space in there. But these different ventricles are going to have a very distinct purpose. And that purpose is going to be cerebrospinal fluid. So let's look into a little more detail, a little more parts and pieces of what cerebrospinal fluid is, what it does, and how it's made. So first off, it is a watery solution very similar to blood because it's made from blood. But you have less protein and a different ion concentration than your normal blood would. So it's a little modified to be specialized for the central nervous system. Now, one of the important functions is buoyancy. The cerebrospinal fluid, or CSF, is going to provide some buoyancy for your brain and for your spinal cord. The reason that's important is your brain, for example, would actually crush under its own weight. If there wasn't the buoyancy from the cerebrospinal fluid, your brain would crush down about a third or so of its size because the structure simply can't hold up itself. It's not made with enough solid protein structures to hold itself in its shape without buoyancy. So it's kind of important to have that to prevent the brain from, in essence, crushing itself. But another function of cerebrospinal fluid is from blows and trauma. So, well, how does that work? The brain has the skull around it. True. But have you ever been in a vehicle and all of a sudden it stops very quickly and your head kind of snaps forward, or maybe it snaps back? You might feel the brain actually move and bounce a little bit. Or if you enjoy roller coasters, some roller coasters have a very sharp turn might make you feel the brain move a little bit. That's because what's happening now is the brain is meant to float inside the skull. There's room to the right, the left, forward, back, up, down, because it's suspended in there. Now, it's not going to have much room, and we're talking small amounts, but there is enough to move a little bit. So by having that buoyancy, that cerebrospinal fluid, it slows down the impact of the brain hitting the side of the skull. Think about it this way. Move your hand through the air. Moves pretty easily, right? Put your hand in water and move it. There's more resistance. It's slower. That's the idea in the brain with the cerebrospinal fluid. As the brain moves, that cerebrospinal fluid has to be moved out of the way to allow the brain to enter that space. So it slows down the impact into the skull just a little bit. So it's helping to protect from sudden stops or jolts of the skull. It's nourishing the brain. We mentioned that the proteins are lower, the ions are different. That's meant to be a special mixture that works for the brain and helps to nourish the brain. It's also going to allow different chemical messengers to travel around wherever the cerebrospinal fluid is located. So we're having a few different things going on here. So when we start looking at how the cerebrospinal fluid is made, you're going to notice the red here, that's going to be all your bloodstream. But notice what's around it, close to it, all these cells. They're all cerebrospinal fluid producing cells. Those are the ependymal cells. So the ependymal cells. The job of the ependymal cells, remember those glial cells we talked about before, but these ependymal cells are going to take that blood, modify it, and then release cerebrospinal fluid. That cerebrospinal fluid then will leave the ventricles to go circulate around the brain and the spinal cord. So here's what we're looking at for the circulation. We're starting in the ventricles. So here's a ventricle, here's a ventricle. We're starting in production there. From there, you can follow the arrows and see how it's heading down right in the middle here. There's this lateral aperture and this median aperture. Those allow the cerebrospinal fluid to leave the confines of inside the brain and head outside to the outside environment around the brain. From there, it can circulate down the spinal cord and around the spinal cord, and go out around the brain as well. Because everything now is connected in the external environment around the brain and spinal cord. Eventually, that cerebrospinal fluid, though, needs to leave. See, it's leaving out here, leaving out here. Those are going to be the arachnoid villi. Now, there's only 2 shown here. There's more than 2 around your brain. It's just an idea to give you an idea of what's going on. But it's leaving through the arachnoid villi to head out to the blood to be recycled. So you're constantly producing, constantly recycling the actual cerebrospinal fluid out in the blood. But sometimes things don't quite work as you want them to. In the case of hydrocephalus is going to be something that is blocking or preventing the reabsorption of cerebrospinal fluid into the blood. It could be swelling that's closing down those arachnoid villi. It could be overproduction of cerebrospinal fluid. You can't get enough out. It could be something got stuck in there and the arachnoid villi just can't get rid of the actual cerebrospinal fluid. It could be a whole series of things. The idea is, though, you cannot adequately get rid of cerebrospinal fluid fast enough compared to what you're producing cerebrospinal fluid. Normally, what you produce and what you get rid of should be pretty much even. If you're producing more than you get rid of, problems arise, hence hydrocephalus. Now, in a newborn, it's going to build up inside the spaces of the brain, but thankfully, the newborn's skull is not fused together yet. Those bones haven't formed their sutures, at least completely, which means the skull is going to be able to kind of almost flex open a little bit. You can see here in this image that newborn's head is larger than it should be. That's because there's building up cerebrospinal fluid out in that subarachnoid space. And therefore, it's just causing everything to stretch out. This can be treated, this can be fixed with proper medical intervention. Now, in the case of an adult, this can be more problematic a whole lot faster. The adult skull, everything is fused together, the sutures are in place. There is no place for the skull to expand. So building up of cerebrospinal fluid in an adult, the only place to go is inward. So it starts compressing and pushing on the brain, basically causing the brain to shrink and push it inside. So in the case of this one, again, if it's diagnosed, medical intervention, you're going to cut a hole in the skull to relieve the pressure. It can be treated, it can be dealt with in most cases. But again, the first thing that needed is make sure you know what the problem is. So in the case of hydrocephalus, too much cerebrospinal fluid causes swelling in an infant or newborn, but adults, all the pressure goes inward. So the ventricles of the brain, looking at cerebrospinal fluid and production, a few things that help the brain in its daily function.